All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is gas laws part 3. If you don't have a calculator handy, then go ahead and pause the video and we'll get started. So here we go. First, a little bit of a background, and that is that if we can combine Boyle's law, Charles law, and Gay-Lussac's law together, we get the combined gas law. P1V1 over T1 is equal to P2V2 over T2. Will tell us the relationship between these variables for a given number of molecules of gas. So remember that if we change that, we're going to have to put an N1 down here and an N2 down here. For now, we'll just leave this as the combined gas law. The ideal gas law is the second major formula we're going to be talking about today, and that's pressure times volume is equal to the number of moles of gas times the gas constant times the temperature. Remember, all temperatures must be in degrees Kelvin, so make sure you know how to do those conversions. So let's just talk a little bit about the gas constant. It says R is the ideal gas law constant, and its value depends on the units used for pressure. Note that T must be in kelvins, and is in moles, and volume is in liters, which is the same thing as a cubic decimeter. So keep that in mind. A liter and a cubic decimeter are the same thing. So examples of the constants values are R is equal to 0.0821, that's liter atmospheres per mole per degree Kelvin, or you can write it as 8.314 liter kilopascals per mole per degree Kelvin. Either way is fine, depending on the units that you're using. So let's do a little bit of practice. Here we go. Number 1 says, how many moles of helium are in a balloon volume 6.452 cubic decimeters at 99.7 kilopascals and 297 degrees Kelvin? Now we need to take very close attention to the units that we're using here. So we've got the volume in decimeters cubed and the pressure in kilopascals. The temperature, fortunately, is in degrees Kelvin. So we're going to use the ideal gas law. Nothing's changing, so we're just going to use PV equal nRT. And so N under this, in this situation, is what we're looking for. We're looking for the number of moles of helium. So we say N is equal to PV equal RT. I simply divided both sides by RT to get that. So N is equal to, so now let's plug in. We've got 99.7 kilopascals times 6.452, that's cubic decimeters, and we'll divide that by R. In this case, we're going to use 8.314 liter kilopascals per mole per degree Kelvin, and we'll divide by the temperature in degrees Kelvin, which is 297. When you divide those, you're going to get N is equal to 0.261 moles of helium. We're done with the first one. Let's look at number 2. It says a rigid 8.77 liter tank contains 1.45 moles of oxygen at 20 degrees Celsius. What is the pressure in atmospheres? So again, nothing's changing, so we're going to use the ideal gas law. We have PV equal nRT. So pressure then is equal to nRT divided by V. I'm just dividing both sides by volume. So pressure is equal to, now let me plug in, 1.45 moles times, this time we're going to use the R of 0.0821 liter atmospheres per mole per degree Kelvin. Remember, the use of the R, the choice of R is going to depend on what other variables, or what are the units of the variables that we're using. So in this case, we're going to be using, again, 0.0821, that's the liter atmospheres per mole per degree Kelvin, times 298 degrees Kelvin, and we'll divide that by the volume of 8.77 liters. So pressure then is 3.98 atmospheres. When you do that division, you get almost 4, but not quite, so that's 3.98 atmospheres. That's number 2. Let's look at number 3. Number 3 says, what is the temperature of 12.2 moles of gas in 18.35 liter tank at 16.4 atmospheres? You're to express that both in degrees Kelvin and Celsius. So when you're simply asked what is the temperature under these circumstances, you're going to use the ideal gas law, the PV equal nRT. So temperature then is equal to, we're going to divide both sides by nR. We get PV divided by nR is the temperature. So let me just plug in. Temperature is 16.4 atmospheres times 18.35 liters divided by 12.2 moles divided by 0.0821 liter atmospheres per mole per degree Kelvin. Temperature then is going to be 300 degrees Kelvin. Remember, this will give you the temperature in degrees Kelvin. 300 degrees Kelvin, we'll subtract 273 to get 27 degrees Celsius. And now we've expressed the temperature both in Kelvin and Celsius degrees. we're done with number 3. So we'll move on. Number 4. Number 4 says the volume of a gas is 200 milliliters at 275 degrees Kelvin with 92.1 kilopascals. Find its volume at STP. So what does STP mean? Well, standard temperature and pressure means that you're at 0 degrees Celsius. That's 273 degrees Kelvin, and you're at 1 atmosphere. That's 101.325 kilopascals. So we're looking to see what the volume is at under a different set of circumstances. We're going to use the combined gas law to do that. So we've got P1V1 over T1 is equal to P2V2 over T2. So V2 then is equal to, I'm just going to align the terms so I get V2 by itself. And here's what I get. P1V1 T2 divided by T1 divided by P2. Check me on that. V2 then is equal to, and I'm just going to plug in, P1 is 92.1 kilopascals, V1 is 200 milliliters. I'm going to have a temperature of 273 Kelvin for T2. T1 is 275 degrees Kelvin, and P2 is 101.325 kilopascals. V2 then is 180 milliliters. Notice that I didn't change the liters to milliliters. I knew that the V2, if the V1 was in milliliters, V2 was going to be in milliliters as well. So I get 180 milliliters as my answer, and I'm done with number 4. Let's go to number 5. Number 5 says, what pressure in kilopascals is exerted by 94.6 grams of CO2 at 57 degrees Celsius in 0.75 cubic decimeters? Well, the first thing we're going to need to do is convert that grams to moles. Remember that the PV equal nRT equation is going to require moles, so let's do that. We've got 94.6 grams over 1 times 1 mole per 44.01 grams. I just added up carbon and 2 oxygens to get that. And I get this number, 2.15 moles of carbon dioxide. That's the number I'll plug in for N. So we get PV equal nRT, that's the ideal gas law. Pressure then is equal to nRT divided by V, right? nRT divided by V, I just pulled the V underneath, and now I'm going to start plugging things in. So pressure then is equal to 2.15 moles times 8.314 liter kilopascals per mole per degree Kelvin, times the temperature of 330 degrees Kelvin, and I'll divide that by the volume of 0.750 cubic decimeters, right? So when I calculate my pressure, everything's going to cancel away except kilopascals, and I get 7,870 kilopascals, and that'll do it for number 5. Last problem, number 6. Here's what it says. It says a sample of propane occupies 250 liters at 125 kilopascals and 38 degrees Celsius. Find its volume at 100 kilopascals and 95 degrees Celsius. All right. Understand that all Celsius degrees are going to have to be converted to Kelvin. Celsius to Kelvin is just adding 273. That's not going to be a big problem, however, but everything else can remain the same. So we have P1V1 over T1 is equal to P2V2 over T2. This is the combined gas law, of course. And we're going to isolate V2. That's what we're going to look. We're looking for the volume under a second set of circumstances. So V2 is equal to P1V1 T2 divided by T1 divided by P2. I'm just going to plug in. P1 was 125 kilopascals. V1 is 250.0 liters times the temperature is 368 degrees Kelvin. Divide that by 311 Kelvin and divide that again by the second pressure, which is 100 kilopascals. When you do that, you get 370 liters. That will do it for the last one. I'll see you in the next one. Thanks. Bye-bye.